So let's discuss the concept of formal charge. Formal charge is a fictitious bookkeeping tool, and I have spelled fictitious wrong. There should be a U in there, but nevertheless it is a fictitious bookkeeping tool. So it's not real, but it is definitely useful. And basically what it is it's the charge that an atom would have if electronegativity differences are ignored. So in the case of hydrogen chloride, we've seen from previous videos that this bond here is going to be polarized towards the chlorine because it's more electronegative. So the chlorine is going to hog up more of that electron density that's shared between these two atoms. However, when we calculate formal charges, the formal charges of both of these atoms turn out to be zero. So let's get into the formula for how to calculate formal charge. To calculate the formal charge of any atom, you take the number of valence electrons that atom has, which if it's a main group element, that's as easy as just looking up the group number. Number of valence electrons minus the number of formal electrons that atom has. So basically what formal electrons are is they can be thought of as electrons that are owned by an individual atom. And the way that we calculate that is we take 2 per lone pair and 1 per shared pair around that atom. So if we go back to the case of hydrogen chloride, the chlorine atom owns all of its lone pair electrons formally, but it owns only one of the electrons that are shared between the two atoms. And the hydrogen also, owns the other electron that's shared between the two atoms. So before I go through a couple of examples, I'd like to go over a couple of rules when working with formal charges. The first rule is that the sum of all your formal charges in your molecule or ion must equal the overall charge of that molecule or ion. So if it's a molecule, then the sum of the formal charges must equal 0. If it's a polyatomic ion, then the sum of the formal charges must equal whatever the charge is of that particular ion. And secondly, the best Lewis structure has the fewest number of non-zero formal charges. So if you have these 2 or 3 competing Lewis structures, you want to choose the one that has the fewer number of non-zero formal charges. Okay? So let's go through a couple of examples where we calculate some formal charges. So this is the Lewis structure for water. Let's calculate the formal charge of every atom in this thing. So let's start with this hydrogen. The formal charge of this hydrogen is going to be the number of valence electrons, which is, whoops, I'm going off the screen here. The formal charge of this hydrogen is going to be the number of valence electrons, which is 1. Hydrogen's in group 1, so it has 1 valence electron, minus the number of formal electrons that it has, which is 2 per lone pair, 1 per shared pair, right? There's only one shared pair, and it's 1 per shared pair, so you'll get 1 minus 1, which is 0. Now let's calculate the formal charge of the oxygen atom. The formal charge of the oxygen atom is going to be the number of valence electrons that atom has, which oxygen is in group 6, so it has 6 valence electrons. And now we have to subtract away the formal electrons. So the formal electrons is going to be 2 per lone pair, 1 per shared pair. Let's start with the lone pairs. There are 2 lone pairs, and it's 2 per lone pair, so 2 times 2 plus the shared pair electrons. There are 2 shared pairs, and it's one electron per shared pair, so it's going to be 1 times 2, 1 per shared pair, and there's 2 shared pairs. So 6 minus the quantity of 2 times 2 plus, so this is going to be 4 plus 2, so this whole term is going to be 6, so it's going to be 6 minus 6, or 0. And the formal charge on this hydrogen is going to be, it's going to turn out being the same as the other one. We're going to get the number of valence electrons, which is 1, minus the number of formal electrons. This hydrogen has the same number of formal electrons than this hydrogen, which is just 1. So the formal charge on all 3 atoms turns out to be 0, which makes sense because this is it's a molecule, so the sum of the formal charges must equal 0, and indeed they do. So let's go over another example. How about the Lewis structure for nitrate ion, NO3 minus? So let's just start from the beginning and just do the Lewis structure completely. So the skeletal structure with the least electronegative atom in the center is going to be this. That is our skeletal structure. And if we count up the total number of electrons in this thing, we'll end up getting nitrogen has 5, oxygen has 6, and there are 3 of them. 6 times 3. And then we have to add 1 electron because there's a negative charge. And that's going to end up being 24 valence electrons. Divide that by 2, we'll get 12 electron pairs. And to start using up these electron pairs, we're going to put 2 electrons in between every 2 atoms. So there's 1 pair, 2 pair, 3 pairs. 12 minus 3 is 9 electron pairs. Now we have to add lone pairs to the more electronegative atoms, giving octets to as many as we can. So we have 9 left, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've used up all the electrons. Now what we have to do is we have to form double bonds as necessary to give octets to everything. Right now all of the oxygen atoms have an octet, but the nitrogen does not. So it looks to me like we can put one of the lone pair electrons from one of the oxygens into the bonding region to make something like this. And now it seems as if everything has an octet. Now let's calculate formal charges. So notice that we have 2 oxygens that appear equivalent, but then we have one that is not equivalent to the other 2. We also have a nitrogen. We have to calculate the formal charge of that thing too. So let's start with that central nitrogen. What is the formal charge of that? So the formal charge of this nitrogen is going to be, let's see, the number of valence electrons that nitrogen has is 5, because it's in group 5, and then 5 minus the number of formal electrons, 2 per lone pair, 1 per shared pair. Looks like there's 1, 2, 3, 4 shared pairs. The double bond counts as 2 shared pairs. Okay, so it looks like we're going to have 5 minus 4, which is equal to positive 1. So the nitrogen doesn't have a 0 formal charge. It has a charge of plus 1. So I'm just going to stick that in right here. Let's start with this oxygen, or let's continue with this oxygen up here. Let's calculate the formal charge on that. The formal charge on this oxygen is going to be, let's see, oxygen has 6 valence electrons minus the number of formal electrons, and 2 per lone pair, 1 per shared pair. Let's start with the lone pairs. There are 2 lone pairs, so 2 times 2. And then we're going to add to that the number of shared pair electrons, and there are 2 shared pairs, so 1 times 2, 2 shared pairs, 1 electron per shared pair. And this kind of looks like the oxygen that we in water, doesn't it? 2 lone pairs, 2 shared pairs. This whole term in brackets is going to be 6. 6 minus 6 equals 0. So the formal charge on this oxygen then is 0. And now we're going to move on to the other 2 oxygens. And it's a safe assumption, since these 2 oxygens are equivalent, that they're going to have like formal charges. That'll always be true. If you have 2 atoms that have the same electrons around them and the same, number of bonds and number of lone pairs and number of shared pairs, then they're going to have the same formal charge. So all we have to do really is calculate the formal charge on one of them, and then we'll have the same, that same formal charge for both of them. So the formal charge then is going to be 6 electrons, 6 valence electrons from oxygen, minus the number of formal electrons. So 2 per lone pair, 1 per shared pair. We have 3 lone pairs, So that's going to be the quantity of 3 times 2. And then we have to add the shared pair electron, and there's one of them. So 3 times 2 plus 1, that's going to be 7. So 6 minus 7, which is equal to minus 1. So the formal charge of each of these oxygens is minus 1. And as we stated before, the total charge on this thing is just minus 1. So we would write it in brackets and give it a superscript minus. And notice that the formal charges in this case also add up to the charge of the ion. 1 minus 1 minus 1 plus 0 is going to be minus 1. So indeed the formal charges, the sum of the formal charges does indeed equal the charge of the polyatomic ion.